Okay, video number 2 for logarithmic differentiation. We're going to start with y equals x to the x minus 1. This equation is not an exponential function, it's not a logarithmic function, so we really don't know how to find the derivative of it yet. You can't just do the simple power rule. You can't take the exponent, x minus 1, bring it down in front, multiply it by x, and then do x minus 1 minus 1. Like you can't use the simple power rule where you take n down in front and then you do n minus 1. That only works if n is a number, not an exponential expression, or not a variable expression. So we're going to start by taking the natural log of both sides. Because that is something I can do for an equation. It doesn't change the values in the equation. So natural log y equals natural log x to the x minus 1. Then we're going to use the properties of logarithms. Say if I have natural log of a value raised to a power, I can bring the power down in front. So I did that and I took the derivative, so I'm kind of doing two steps at once. But just to show that. So from just this part, natural log x, x minus 1, I rewrote right there x minus 1 times natural log x, because that's just that property of logarithms. So when I take the derivative of both sides, on the left-hand side I get 1 over y times y prime, or dy dx. On the right-hand side, I'm going to use the product rule. So the derivative of x minus 1 is 1 times natural log x, plus the derivative of natural log x is 1 over x times x minus 1. So this right-hand side is the product rule. Then I multiply both sides by y and plug in what y actually is. And I don't really need to clean that up. I could write it as a single fraction, but it really doesn't become any prettier. So I'm just going to leave it as natural log x plus x minus 1 over x, and then all times x to the x minus 1. So you wouldn't have ever come up with that just on your own using the simple power rule or a combination of simple power rule and anything else. So a problem like this where you have a variable expression as your base and a variable expression as your exponent, you have to use logarithmic differentiation. Before I get into the other main use for logarithmic differentiation, I would point out a property. And I don't want to read this off to you because you can read it. But essentially, when you're working with logarithmic expressions, you're going to see absolute values, especially, and the reason they say natural log u is because u represents some function. So if I said natural log of x squared, u would equal x squared. If I said natural log of 2x plus 5, the 2x plus 5 is my u. So a lot of times you'll see absolute value bars after the natural log because you can only take the natural log of positive numbers. Right? If you look at y equals natural log x, it has a vertical asymptote at x equals 0. And so the domain of that function is all positive values of x, so not 0, because 0 is not positive or negative. So when you take the derivative with natural log, and they have an absolute value there showing that they want it to always be a positive value, like they want the natural log of something, the something has to always be a positive value. They'll put the absolute value bars there. When you take the derivative, you just take the derivative. We've probably already done that without really paying attention to it. We said, y equals natural log x. The derivative of that is 1 over x. And I guess we just kept in the background in our mind the fact that what's the domain of natural log x. So this is just making it more clear. So here's an example of what that looks like. Now we're going to use the cosine function. We haven't talked about the derivative of the trig functions yet. I have this example in here because in the past I've done the trig derivatives first, but the derivative of cosine is negative cosine. That's not true, sorry. The derivative of cosine is negative sine. So this is just a chain rule. And the reason we have that cosine x in parentheses or in absolute values is to make sure that we can take the derivative of all values of x. If I look at Desmos and I graph y equals natural log of the cosine of x, Notice I have a bunch of values missing on my graph, and I could zoom out, but that's not going to change it because we know that cosine is positive from 0 to pi over 2, and then from pi over 2 to negative pi over 2, or pi over 2 to 3 pi over 2, cosine's negative. So if I look at x equals pi over 2, that's where I stop getting, you know, values for my black function. And if I take that all the way to 3 pi over 2, okay, that's where I start getting black values or functions for my black values for my black function, y equals natural log cosine x. So I'm missing things. So instead, if I put parentheses around it, actually it doesn't like how I'm typing that in, so I'm going to do this again. Y equals, oh, I put my parentheses in the wrong spot. Natural log of the absolute value of cosine x. Now, when I take the absolute value of cosine, um, because sometimes cosine's positive, sometimes cosine's negative. When I take the absolute value, I get only the positive values. So now I can take the natural log for any value of x plugged into cosine x. So it does, my domain is not limited for values of x anymore. So again, we use the absolute value bars there to give us a full range, sorry, a full set of values to use in the domain. Cosine x, I can plug in any number I want for x because cosine doesn't have a limit on its domain. The range for cosine x is going to be positive or negative. So putting in the absolute value there ensures that I can take the natural log of this no matter what goes in for x. The derivative of natural log of something is 1 over something times the derivative of the something. So 1 over cosine x times negative sine x, which would just be y equals negative tangent x. So the absolute value bars, again, you kind of ignore them and you just take the derivative normally, but the absolute value bars are there for a reason so that your um, domain of y as a function of x is not limited. We see that mostly with composite functions. Okay, 7 minutes 42 seconds into the video, we're going to finally see the real reason we're doing this. Um, the second lesson with logarithmic differentiation is mainly used to learn how to take the derivative of exponential and logarithm functions that have a base that is not e. But again, remember everything that we've done so far is based on the natural base. Just being clever with words today, right? All right, so just to solve this, we're going to use logarithmic differentiation. By solve it, I mean take the derivative. So to find the derivative, take natural log of both sides, right? Then we use properties of logarithms to rewrite that power down in front. So natural log y equals x natural log 2. Then I take derivative of both sides. What's interesting about this is this looks maybe like the product rule on the right-hand side, but it's not because natural log 2 is just a number. So on the right-hand side, I just have a number times x. So on the left-hand side, I have 1 over y times y prime, or dy dx. And on the right-hand side, the derivative of x times natural log 2 is just natural log 2. Natural log 2 is just a number. It's like a, whatever number it is. I was going to say 5, but it's making up a number in my head. So anyway, natural log 2, it's just that constant. I multiply both sides by y, and then I replace the y value. So this wound up, the derivative of 2 to the x is natural log 2 times 2 to the x. And if I started with 5 to the x, then my derivative would be natural log 5 times 5 to the x. So in general, for y equals a to the x, if I do that exact same process, and I literally just went back into my program I was typing and I changed all my 2's to a's. For y equals a to the x, the derivative is natural log a times a to the x. So you can go ahead and pause, kind of take down those notes, look through that, make sure you're comfortable with that. We can also do this for a logarithm with a base of a. Remember that change of base formula? Told you had a lot of good uses. Well, one of them is this. You can change the base to natural base. So change the base to e because we know how to work with the natural base. So log base a of x is really natural log x over natural log a. Natural log a is just a number, right? So if I want the derivative of y equals, or f of x equals log base a of x, I can rewrite that as natural log x over natural log a. Remember, natural log a is just a constant, or 1 over natural log a is just a constant for whatever a happens to be. So if I take the derivative, then I have that constant times 1 over x. Right, I kind of separate it out there. So there's my constant, 1 over natural log a times natural log x. And so my derivative is 1 over natural log a times 1 over x. So working with a different base, like 2, if this was log base 2 of x, I would just have 1 over natural log 2 times 1 over x. Here's kind of a summary slide using the chain rule idea. Again, u represents any function of x. So e to the u, we've already done. E to the u times u prime. Natural log u is 1 over the function times the derivative of the function. Now with a different base, a, so if it's like a 2 like we did, so it's natural log a times a to the u times u prime. So um, it would be natural log 2 times 2 to the x, or whatever that function is, and then log base a is on the bottom. So you can refer back to those. Those are your formulas for everything we've done so far in this new unit with derivatives for exponentials and logs. We're not going to do any other ones. The rest of the stuff we're going to do is trig. And then let's try some of these together. So y equals 4 to the 5x, and I'm going to bring up my typing program. Some of you guys have logged on and talked to me, asked me some questions, and I've been using this math type. Okay, so if y equals 4 to the 5x, what I could, write natural log y equals natural log 4 to the 5x. And then I can take the derivative of both sides. That's logarithmic differentiation. That's what I would do if I didn't know the rule. So maybe that's what we do for this first one. So natural log y equals natural log 4 to the 5x. So take the derivative of both sides. Right? And then and I guess actually before we did that, we could say natural log 4 to the 5x is the same thing as 5x times natural log 4. Usually we write it in front, and I can do that if that makes you happy. On this one though, I'm going to write it second, just to show that nice commutative property of multiplication, but really because I want the natural log 4 in front because it's just a constant. So the derivative of natural log y is 1 over y times y prime. And then on the right-hand side, derivative of natural log 4 times 5x is natural log 4 times 5, because that's all constant. So then y prime is going to be natural log 4 times 5, or 5 natural log 4 is a nice way to write that, times y. And y is on my screen right there to the left, so 4 to the 5x. So I'm going to capture all of that in, so I can save it. Sorry for the loud camera click there. Oh, it looks like I got the little blinking white line, black line, whatever. So it's there. But again, and I'm going to bring my typing tool back up. If I just wanted to apply the rule, okay, go through it that way, we could say, okay, we have this base 4, so y prime is going to equal natural log 4 times the original function, 4 to the 5x, times the derivative of the power in that function, so times 5. You can see it, that natural log 4 times 5 comes together to be 5 natural log 4. I'm going to go back a slide and again show this rule, highlight what I'm talking about. Okay, so for this problem, we had 4 to the 5x. So we have a natural log of 4, that's that first part, natural log a, times the original function, 4 to the 5x, and then using the chain rule, times the derivative of the 5x, which was just 5. All right, for the second one, we have log base 3 of x. See if I can get this over here. There we go. All right, log base 3 of x. So my derivative is going to be, if I just try to use the property, if I just try to use the property in the previous slide, it's going to be 1 over natural log 3. And I don't use these so often that I just have them memorized. Every year it's kind of like I re-memorize them. But if I'm looking at this one, I'm trying to think through, well, how would I just know that rule? It goes back to, where did it come from? Well, we took the we actually didn't take the natural log of both sides. What we did was we said log base 3 of x. We're going to rewrite that as log of natural log x over natural log 3. So the over natural log 3 is already there. And now I'm taking the derivative of natural log x, which is 1 over x. And I think that's it. But let's check. Let's put that in there and then check my rule and see if I got it right. Again, sorry for the camera noise. All right. So my rule for this one, okay, natural log a to the u is 1 over natural log a, so 1 over natural log 3 times 1 over u, which was 1 over x, times u prime. Well, the derivative of x is just 1. So it does follow that rule. And if you wanted to go back to, whoops, I want that. If you wanted to go back to looking at it the long way, like if I didn't want to use the rule, then I would say, well, y equals change of base. So natural log x over natural log 3, which you could write as 1 over natural log 3 times natural log x. So if you took the derivative, dy dx would equal, okay, 1 over x times the constant that's there, and then times the derivative of x, which is just 1, so 1 over natural log 3. Because that's just a constant in front. So for that one, it is what it is. All right, and then for our third one, we have x squared times log x. So remember, log x is log base 10. So this is going to be a product rule. So my derivative is going to equal, the derivative of x squared is 2x. So derivative of the first times the second, so times log x. I don't know why I just made a bunch of noise there. Okay, 2x times log x plus the derivative of log x. That's log base 10 of x. So derivative of that's going to be 1 over 10 times 1 over x, because it's natural log of x over natural log of 10. So 1 over natural log 10 times 1 over x, and then times the original function, or times the first function, which was x squared. So that means my derivative equals, again, 2x log x plus, clean that up a little bit and just say x over natural log 10. Copy that in. Okay, so x squared log x becomes 2x log x plus x over natural log 10. And we're at 20 minutes, so I'm going to stop there. I'm going to make sure that I did that last one right. But I'm going to stop there, and that should be enough to get you through what we're doing today. Our Google Meet schedule for this week is posted online. I'll post another one next week online, probably going to be similar to this week. I've been having meetings with other teachers and coaches and different things like that, so sometimes that gets in the way. But good luck. Have a good week, guys.